Hello, this is Dr. Glasbrenner from George Mason University, and in this video, we will discuss what it means when a data collection method utilizes data sampling and how it affects what we can infer after analyzing a data set. In a previous lecture, we reviewed several methods of data collection, but we did not explain how to handle data collection when it is not easy or possible to gather all measurements on a target population that might be relevant for a scientific study. Instead, researchers will gather a subset of cases, often a small fraction, which is called a sample. Sampling is a natural human activity. A simple analogy is to liken sampling data from a population to taking a taste of a pot of soup that you are cooking. You want to figure out how the soup is doing, so you taste a small part of it to get an idea of how it's doing as a whole. Now, when you taste a spoonful of soup and decide the spoonful you tasted isn't salty enough, that's exploratory analysis. If you generalize and conclude that the entire soup needs salt, that's an inference. For your inference to be valid, the spoonful you tasted, the sample, needs to be representative of the entire pot, or the population. If your spoonful comes only from the surface and any salt you added is collected at the bottom of the pot, what you tasted is probably not representative of the whole pot. If you first stir the soup thoroughly before you taste, your spoonful will be more likely to be representative of the whole pot. As you can see, the representative sample allowed us to infer a conclusion and then take action as needed, but this only works if our sample truly lets us generalize to the full population. The soup analogy may make it sound easy, but there are many things that can impact whether or not it's possible to generalize. To illustrate, let's consider some examples. Here's an example taken from a New York Times article that reported on an experiment testing a research question. Can people become better, more efficient runners on their own simply by running? If you were asked to critically examine how this question is addressed in the study, there are some questions you should consider while you read. To begin, ask yourself, what is the population of interest? This should be based on the way the research question is phrased. In this example, the question is general and the population of interest would be all people. Next, look and see what the characteristics are of the study sample. For this article, the sample is a group of adult women who recently joined a running group. Now, ask yourself, based on the sample characteristics, what is the population to which the results can be generalized? The answer would be adult women if the data are randomly sampled. So, as constructed, the study sample does not allow us to infer the answer to the research question as it is not representative of the full population. Yet, as you might guess, this doesn't mean people won't go ahead and make unwarranted conclusions anyway. Consider the following historical example. Anti-smoking research started in the 1930s and 1940s when cigarette smoking became increasingly popular. While some smokers seemed to be sensitive to cigarette smoke, others were completely unaffected, and these research programs were faced with resistance based on anecdotal evidence such as, quote, "My uncle smokes 3 packs a day and he's in perfectly good health," end quote, which represent a limited sample size that might not be representative of the population. Early research on smoking continued to encounter difficulties in linking smoking to poor health outcomes, due in large part to the difficulty in gathering a representative sample, as smoking is a complex human behavior confounded by human variability. However, over time, this problem receded as researchers were able to analyze larger samples of cases, and the trend showing that smoking has negative health impacts became much clearer. With these examples in mind, you might wonder why it is that we use sampling at all. Wouldn't it just be better to just try and gather observations for the entire population and avoid all these pitfalls? Let's consider it. Doing this is called taking a census, and while it sounds appealing, there are problems with doing this. In practice, it is difficult to complete a census, as there always seem to be some individuals that are hard to locate or measure, and these difficult to find people may have certain characteristics that distinguish them from the rest of the population, meaning you can't ignore them. Furthermore, populations rarely stand still. Even if you could take a census, the population changes constantly, so it's never possible to get a perfect measure. There are many complications with taking a census that make it more reasonable, even when there are many things that can go wrong, to collect a representative sample instead. Let's consider some of the mechanisms that can lead to a sample becoming biased such that it is no longer representative. Continuing with examples involving people responding to surveys. One source of bias is non-response, which means that only a small fraction of the randomly sampled people chose to respond to a survey. Another source of bias is voluntary response, which occurs when the sample consists of people that volunteer to respond because they have strong opinions on the issue. This situation applies to non-scientific internet polls, for example. Yet another source of bias is the convenience sample, which means there are certain kinds of people that are easier to access and thus are more likely to be included in the sample, even when you sample randomly. These types of biasing mechanisms were at play in the following historical example. In 1936, Landon sought the Republican presidential nomination opposing the re-election of Franklin Delano Roosevelt. Not unlike what we see today, various publications wanted to try and forecast the results of this election. The Literary Digest attempted to do this by polling 10 million Americans about who they were going to vote for. They received responses from about 2.4 million, which is significantly higher than most polls. The poll showed that Landon would likely be the overwhelming winner, and FDR would get only 43% of the votes. Yet, we know that is not how history played out. Instead, the election result was that Franklin Roosevelt won with 62% of the votes. This forecasting error completely discredited the magazine among the general public, and it was soon discontinued as a result. So what went wrong? Why would a dataset containing 2.4 million responses be so biased? It becomes clear when we take a look at how they selected those 10 million Americans for this survey. The magazine surveyed its own readers, registered automobile owners, and registered telephone users. This means that the magazine was sampling groups with incomes well above the national average of the day. Remember, this is the Great Depression era, which resulted in lists of voters far more likely to support Republicans than a truly typical voter of the time. In other words, the sample was not representative of the American population at the time. While this is a story that happened over 80 years ago, it is a cautionary tale that has become even more relevant in the age of big data. Large samples are preferable, but they are worthless if they are biased and lead to inaccurate predictions. Returning to our soup analogy, if our soup is not well stirred, then it doesn't matter how large a spoon you have when you sample it. It will still not taste right. If instead the soup is well stirred, then a small spoon will suffice to test the soup. To wrap up, even when you have a randomly sampled population and your sample is representative, and you also find a trend, you may not be able to establish causality. This is what is meant by the phrase, correlation does not imply causation. Being able to establish a causal mechanism requires conducting a controlled experiment. Otherwise, it is not possible to determine if you are seeing a cause and effect relationship in a dataset or if you are observing a correlation, meaning two effects that move in tandem due to an underlying cause you have not identified.